What is up, YouTube? So today we'll discuss the WebSocket protocol and we'll also discuss its pros and cons. You've probably heard about WebSockets before, but we'll dive into a certain level of depth so we can understand it better. So WebSockets. So the motivation behind WebSockets, let's talk about that. HTTP is considered the de facto for web APIs, and it's considered the best option for executing batch tasks asynchronously. But for two-way and real-time communication, such as chat, live streaming, gaming, HTTP falls short since it's a request response protocol. And here are some HTTP-based techniques and their corresponding limitations in achieving bidirectional communication, right? So this table specifically that we're going to look at only focuses on HTTP version 1.1 since the other versions didn't exist when WebSockets were first developed and introduced. So here we have short polling, and in short polling, request frequently for updates from the server. So a client will request frequently from the server after fixed short intervals, and the server responds whether it has an update or not. And the problem here is too many unnecessary requests for updates. And then we have long polling. So basically the client requests for updates from the server with the channel left open, and based on some constraints, and when the server responds, or the server will respond when it has an update, right? And as HTTP follows a request response model, and as a result it uses multiple concurrent connections for sending data and receiving updates, and this will lead to resource wastage. And then we have HTTP streaming. So streaming allows servers to stream bytes of data continuously over a single connection to the client while keeping the connection open. And this suffers from half duplex communication. So only one party can send at a time, right? And we want to have full duplex where each server client can send their data at any point, right? And so, because of these limitations from HTTP, we needed a different approach to achieve two-way data transfer. And it needs to be low latency and avoid TCP handshakes by keeping the connection open indefinitely. So, what is a WebSocket? A WebSocket was first introduced in 2011 to enable full duplex asynchronous communication over a single TCP connection to use resources efficiently. Half duplex communication, so in this case, a client first sends a request to the server and it responds to it, right? And WebSockets take full advantage of the TCP connection, allowing clients and servers to send or receive data on demand. So here we have half duplex. So the client sends a request, and after that, the server can send a response, right? And then there's request, response, right? It's not like the client can send a request whenever and the server can send a response whenever. There's it's like kind of one way, if that makes sense. And then we have full duplex, where the server can send data whenever and the client can send data whenever. And that's what we actually want. And that's what we achieve with WebSockets, right? So, WebSocket is a stateful protocol that performs relatively faster than HTTP because it's lightweight and it carries the overhead of large headers with each request, right? HTTP isn't stateful, and that's why it has to have such large headers so the server can know who the client is and all these different things. And so a WebSocket establishes an HTTP connection, and then it upgrades it to a WebSocket protocol. So all transmissions happen directly on the TCP channel. So URLs for connections with WebSocket begin with WS and WSS for non-TLS and TLS based connections, right? So here we have a picture where first we establish a TCP connection. So here you have your client, and then you have your server on this side, and we have our client that tries to connect with our server using HTTP and on top of TCP, right? And then we send an upgrade header using our TCP or our HTTP connection, right? And it'll upgrade it to a WebSocket, which is bidirectional, right? So, yeah. So I think we just covered this. Move on. So how does it work? So it starts with an HTTP connection established through a three-way TCP handshake, and an HTTP GET request is initiated to switch the protocol to WebSocket, right? The connection upgrade request can be accepted or rejected by the server, and if the server is compatible with the WebSocket protocol and the upgrade request is valid, the connection is upgraded to a WebSocket connection, right? And the response contains the status code 101 switching protocols, right, from the server, and the value for the field is SEC WebSocket accept, right? And let's talk about the upgrade headers. So the headers contain the following fields. It has the status code 101 to show that the protocol is successfully upgraded and can send WebSocket frames. So here we have our upgrade request. So this is the request. It has a connection upgrade right here. It specifies WebSocket, and it looks like we have some key, which we'll talk about. And yeah, then we have our request, which we spoke about, our 101 status code. It has switching protocols. And we also have another key, which we'll talk about. So the SEC socket or SEC WebSocket key, right, is a base64 encoded 16-byte value that the server uses to verify that the upgrade request is coming from a legitimate client that understands the WebSocket protocol. So it's not some malformed HTTP request. And this value is then encrypted using a hashing algorithm like SHA, MD5, and so on, right? And then the server will decrypt the value of our SEC WebSocket key and generates the SEC WebSocket accept field by prepending the globally unique identifier GUID value to the client provided SEC WebSocket key. And the WebSocket accept field is also encrypted and sent back to the client, indicating that the server has accepted the connection upgrade, right? And so are WebSockets and network sockets the same? Well, no, they're not. Network sockets provide API access to the underlying transport layer, which can be TCP, UDP, SCTP, and so on, with aided abstraction, right? So, actual network sockets are a little bit like more lower level than a WebSocket. And a WebSocket is a protocol that allows web applications to communicate bidirectionally over a single TCP connection, right? And why shouldn't we use WebSockets directly instead of starting with a HTTP connection, right? I think this is a good question, right? Well, almost all web servers support HTTP, right? And we can safely fall back to an HTTP request in case the server doesn't support WebSockets and the device can still communicate, right? So how does the client know it requires a WebSocket connection in a particular scenario? So, well, that's up to the developers, right? So the developers of the client-side application, they're responsible for initializing the upgrade requests, right? So this is definitely a design decision that has to be made before developing the front end of the application. Okay. So once the connection is established and upgraded to a WebSocket protocol, initial control frames are exchanged, right? So a WebSocket has two types of frames. It has control frames, which are used to know the status of the connection and can carry a maximum of 125 bytes of payload. And then you have data frames, which are frames that are also packaged with application data. So it's identified by an opcode whose most significant bit is 0. And each frame is identified by a 4-bit opcode, right? So here are a list of common frames and their brief descriptions. So here we have a text frame, and it's a data type. It has an opcode of 1, and this indicates that the information carried by the frame is just text. And then you have a binary frame, also data, opcode 2, and it indicates that information is in this frame is binary, right? And then you have ping, which is a control frame, opcode 8, and usually it's sent by the server to check if the client is still alive. You have pong, opcode 9, and it's used to acknowledge a ping frame when the connection is still live. Then you have the close frame with an opcode of A. And so both endpoints exchange close frames for terminating the connection, right? So there are different types of frames. And so when closing a WebSocket connection, close frames are exchanged between endpoints. And after an endpoint receives a closed frame, it must not send any more data. Any metadata stored to maintain the TCP connection information must also be cleaned up during the connection teardown process by both endpoints. And finally, under normal circumstances, the server raises the fin flag and both endpoints close the TCP connection when the close sequence is completed, right? So here we have a picture. TCP connection is established. Then we upgrade to a WebSocket. And next step, control frames are exchanged and data frames are transmitted by the server, right? And so then closing frames are exchanged and then the TCP connection is closed, right? So that's like the whole life cycle of a WebSocket. So why is it difficult to scale a WebSocket horizontally? Well, okay. So due to the stateful nature of WebSockets, both endpoints are bound to the channel, and we can't have more machines to reroute requests and distribute the workload among different servers, right? And distributing different WebSocket connections to different servers can be achieved by an appropriate intermediary, right? Such as a load balancer or an API gateway. And let's talk about the advantages of using WebSocket. So they perform well for real-time applications and provide these following benefits. It obviously has bidirectional communication, and both the server and client can send and receive data on demand. There's a higher frequency of data exchange. There's also a faster data transmission with a header size of 2 to 10 bytes, right? And it has compatibility with existing infrastructure since it's on top of HTTP, and we can bypass firewalls using the default ports 80 and 443. And let's discuss its disadvantages. So it's a pretty new concept and it's not as mature as HTTP, but it's really good for specific scenarios such as multiplayer gaming, live streaming, video conferencing, chatting, things like that, right? But it does have limitations such as horizontal scaling is pretty complex, right? You can't load balance and reroute requests coming from a client once the connection has been upgraded, right? So say you connect your server, or you're a client and you connect to a server, right? And you have, for some reason, as the client, you have, tons of requests to make or tons of things you need responses to. At that point, the server that you're connected to can't, delegate the work out, right? It's not like, that's why we need to have like a load balancer in between. Um, well, a load balancer will simply just like route to a good server that's open. But if you're a client and you have a lot of demand, right? Or you're sending out a lot of requests, then that server just has to kind of put up with it, right? And so it's definitely greatly affected by connection failures. And the connection is stateful, and the request headers carry no information about sending and receiving ends, right? So it's difficult to recover the lost connection. And yeah, that's it for WebSockets. Hopefully you learned something, and thanks a lot for watching.